Hello and good morning, everybody. Welcome back to our new episode lecture in the course of computer vision. We will look at a new topic today, object detection. But before that, we look at some problems, what can go wrong when you try to train deeper neural networks so that you get some more insights that will help you with the homework. I would also like to start with a quick overview of the solution to last week's homework, as you will, last week's exercise, as you will need that to continue then your homework. So let's have a look at that. So last week we looked at convolutional neural networks for texture segmentation or for semantic segmentation, and we had in the exercise one such neural network that gets as input images, then labels for each pixel of the image, and then the network should try to categorize each pixel with that label. So in our first network, we used just two classes, and we used something that is called padding equals to same, which keeps the images of the same shape. And your exercise was to modify those networks to use more than two classes and to use valid padding. So what do you have to change for valid padding? Well, first of all, you just have to change the padding parameter here to valid, and then it will automatically use the valid padding. And the result of that is that your images will get smaller and smaller because your filter kernel will not fit completely in the image. So if you create this network here with three convolutional layers of size 3 by 3 and valid padding, then we expect that after each convolutional layer, the image will be 2 pixels smaller because there will be a border of 1 where that cannot be processed on both sides. You can see that if you look at the summary here, that the input first is 128 by 128, but after the first convolutional step, it's 126 by 126. And then after each one, it goes down here. The other change that we have to make was for more than two classes. So if we want to have more than two classes, then what do we need to adjust? We need to adjust the last layers. First of all, the last layer should have as output in the channels the number of classes. So for two classes, it's possible just to use a 1 by 1 layer and then use a sigmoid activation function as between 0 and 1. This can also be two classes, but if you have more than two classes, you will use really a channel with the number of classes here, and the activation function has to be changed to softmax. The result of that is that as output here, you will get a vector with the number of size, the number of classes. So for example, four classes, and each entry in that vector will be the probability of that class. Softmax ensures that the scaling will sum up to 1 so that you can interpret it as a probability. So this is all we have to do on that side. But now we have to make one more change because our output is smaller now here, and we want to compare it to our label. So when we generate the label, we have to make sure that the label is also of this smaller size. I usually do this by having this function that creates the neural network return the border that it produces. So this would be the amount of pixels that get cut off from each side. And if you have that, you can just use that to also cut out the label image. So here, use those batch generator that we had at the beginning. This is just we produce the normal image as before, and then here we cut out the label image, cutting out one border at each side and in each dimension. Okay, and then the images match again. If you don't do that, you will get an error when you try to train the network that the size does not fit. And so we can just run that, and then I just run some steps that were not yet enough, so loss function is still going down and the accuracy is not yet very good, but it will be a start, and you can continue for that. Okay, so that would be for the exercise from last week. Any questions for that? Moment. Does not seem to be the case. So what we want to look at next is at some issues of how to train deep neural networks. Yes, I think that some of you probably are quite familiar with this topic and have heard it before, but like I think half of you might not have had so much other lectures about neural networks before. So sorry, please excuse me if for you this is a repetition, but I hope for the others then it will be of some benefit here. Okay, so when you do training of neural network, what can go wrong with your training, and what can you do about it? So there are also always these nice tutorials on the web. You download the data set and the neural network, it all works just perfectly. But when you actually do this and some new data set, then it's not always that easy, and it's possible that just it doesn't happen the way you expect it to happen, and then there's the question of what can you change. So for example, if your model just does not converge at the beginning and nothing happens, what would you do? What are the possibilities that you could change there? Any ideas? Okay, one was more data. I'm not so sure, but let me explain. More data is always good to then get a better result of your network. But if your network does not converge in the beginning, then maybe more data doesn't help. Because if you have little data, it will overfit, but that actually makes it easier for the network. So more data is a good idea, but it's something that you can add later when you don't get as good as results as you expected. You could, somebody mentioned increase the step size. Yes, so if your learning doesn't work at training, then maybe something is wrong with your optimizer, and then this is a good parameter to start step size. Somebody says initialize weights. Yes, we will see that too. If you have a wrong initialization, then it can be that just nothing happens. And then you can play around with that. That's not always that easy. So at the beginning, I would use the initialization as is done by default in your environment. But if it doesn't work, you have to look at that. Okay, somebody said deeper network. Yes. Or maybe less deep network, depending what you start with. So that's also a good question of what is the correct size or depth of your networks here. So let's look at some of this issue. Yes, so we have deeper neural networks, so we want to use in image processing deeper neural networks. Maybe again, from a deep learning perspective, what does it mean to have a deeper neural network? With like a normal neural network, a normal neural network is like a classifier, so it just has some features and then it learns to predict the output. A deep neural network is something that we actually call representation learning. So in image processing, the idea is you have raw input like pixel values, and the network first tries to come up with the features that it needs to do the classification, and then also learns the classification. So it must learn both the features and the classification. So that's why it needs a deeper neural network. But how deep should it be? And maybe we have other possibility. It could be wider with more channels, more neurons per layer, at the end more filter operation. So the question is how large, deep or wide should the network then be? I try to make some quick illustration here to get some feeling for that. So let's see maybe what happens when we try to do a training with a neural network. So initially we are at this position here. We have a function f from x, which is called the data generating function. So this is actually the function that we would like to try to approximate. So you could also say here it's more a regression problem, but the same is true for a classification. The problem is we do not have this function, but we would like that the neural network approximates this function. What we have instead is just samples of these functions at some specific points. So it looks like that. And from that input, the neural network has to learn a function. And of course, it will probably learn something that is close or goes through all these data points here. But there are multiple possibilities here. So here, for example, you have a green function that goes to all of the points, but it varies quite a lot. So maybe that's not so good. Or you have this purple function here that's almost a straight line. It goes in the proximity of most of the points, but it doesn't go through them. But on the other hand, it does not wiggle around so much. So how do you decide which of these functions is correct? From your training data here, you cannot decide that. So you need a second data set, test data or validation data, that has been produced by your same data generating function, but has not been used for training. And so then you could look at how well your function approximates your test data and see how it performs there. And from that, you can measure if maybe it was good or not so good what you did with your network. So we see, for example, here that the green function is too far away from your test data to be a good solution, and the purple function was probably a better solution. So what does it have to do with the depth of the network? If you have a deeper network or also just more capacity, more parameters in your network, then you will have more something like this green function that can adapt to the data, while if you have less capacity, you're more like the purple function here. Okay, so in order to find out if your network has the correct capacity, you need to look at some validation data or test data. So you can have two types of errors then. You can have an error on your training set, and you can have what is called a generalization error, which is the gap between the error on the training and of the test set. If you have a large error on the training set, what does that mean? It means your network cannot approximate the training data, so it probably has too low a capacity, so it cannot go through all the points. So if you have this here, you will have to increase the capacity of your network. While if you have the generalization error, you probably have too much capacity and you should reduce it, or have some other measures to reduce the number of freedoms in your network. So you will have some optimal capacity here between where you have the least generalization error. So like in the beginning, if you don't have much capacity, a generalization error will be, you will just have a large error in the training set, And if you have too much capacity, you will do overfitting. So you will have a small error in the training set, but a larger error in the test set, and so you have a larger generalization error. So more variance, also sometimes this is called more variance. This means that if you change a little bit on your input data, on your training data, your solution will adapt quite quickly to it. While if you have less capacity and you change something on your input data, your function will not change very much, even if you change the data here. Okay, so what can you do to limit the capacity of the network? Well, of course you can just make it smaller, but sometimes, especially in image processing, you want deeper neural network for other reasons. So for example, you have a sequence of filters in the networks, and this sequence of filter will process a larger area around your pixel of interest, and so you need a certain depth just to get this influence region for your pixel here. So if you cannot make the network smaller, there is other possibilities to limit the capacity, and one such possibility is regularization. So how does regularization work? You add a parameter norm as a penalty to the loss function. So what does this mean? It means we have a loss function, which is what we try to minimize. Okay, we have seen last time that could be the Course entropy. And to this loss function, we add another term, and this term is dependent on the weights and on some parameter here. And a popular regularization term is the L2 norm. We will just see that will try to make the weights small, as small as possible. So when you look at that with your loss function, then you might have some optimal weight that you have without the regularization, which is the minimum of the original loss function. And then when you just look at the regularization term, the minimum of the regularization term would be that the weights are actually 0. And so between those two, you have kind of a balance that your resulting weight will be between 0 and the weight that you would have without the regularization. L2 regularization is what's most commonly used. So this will just be the norm of the weights themselves. As a result, this will try to make the weights closer to 0, but all at the same time, so they will not actually go to 0. When you look at that through your optimization, in the optimization, you will do a gradient descent. So what you would have to look at is what happens in the loss function when you calculate the gradient, and you will have the gradient of your normal loss function plus the term here from the regularization, which means you move something approximately to the alpha, the regularization term, times the weight itself. So the larger the weight, the faster you move it to 0 here. So this will in the end balance out. There is also other possible regularization. One is L1 regularization, which just uses the L1 norm here. So this is just the norm of the weight instead of the square. So what happens then when you do the derivation here and the gradient is you get this term here. So here in this regularization, you will always move the loss function by an amount of alpha, either in the direction of the sign of the weight or in the opposite direction, but not depending on the weight. The effect of that is that some of the weights will go to 0 and some of the weights will go to 1. So they will kind of be like sparse weights, and this can also be helpful in other circumstances. So for example, if you want to reduce the number of computations, for example, if you want to deploy it on a mobile device, then if you do L1 regularization, you get sparser data, and this would help in the computation. Other regularization techniques that you can use are so-called ensemble methods, and dropout is kind of an ensemble method in that. What is an ensemble method is you use several models that are trained separately and then kind of vote on the results. So maybe you train 5 networks, you let them all run and then see, okay, 3 of them say it's that class, 2 of them say it's another class. Let's take the majority, what 3 of them say. And dropout implicitly makes some different networks during training. First, it looks a bit like a crazy idea here. So you randomly drop a node in the hidden layer, but rather actually a connection between 2 layers here. So it would be that like the result of that node is just always 0. And this means that this node is not available for the computation. And the result of that is that the network has to learn what could it achieve without that node, but next time maybe it's another node that is not here, so it will have to try like some redundant connections on the network here. So for example, if you have, this is your base network and you have dropout, then each time one of those connections or more of those connections will be 0, and this will effectively means you will have to learn all of these networks here. Some of them will not work, but some here will work, and then you have like an ensemble of all of those that have to be work together to compute the solution here. Okay, another kind of regularization technique is early stopping, which means you will just watch your training and you will stop when the error on the validation set starts to increase again. So what this effectively means is that you learn the number of training steps, because then during test time, and maybe you increase the training data set, and when you want to have your final model, then you will just have learned how many training steps are needed for that. So kind of looks like that. So if your training set loss gets smaller, and smaller, but your validation set loss just remains the same here or even goes up again, then it really is not necessary to train here for over 200 epochs, because already here you have the best result. One of my example, which was clearly shows a nice some overfitting for some game where we trade a neural network for Yassen to declare Trump, and so you see just training goes up and up. It will almost go up to 100%, while the accuracy then on the validation set drops here. So the optimal value would be around here. Personally, I don't really like so much to use this step. I would rather try to use other regularization terms so that the validation actually at least stays the same here. So I think it makes it a bit more robust. But it's always a good measure to watch to see how many steps you actually need for the training. So one other aspect in training these deep models is that it's not actually an optimization problem. What do we mean by that? So what we actually try to maximize is some performance measure on the test set, like the accuracy that we get on the test set. But this is not the function we optimize. Instead, we optimize the loss function. It might be related to our accuracy, but that's not always directly the case. For example, we could also use some other measure like a recall or F1 score here as a performance measure. So by optimizing a loss function, we want to get an optimal performance measure. And of course, we would like to optimize the expected loss over the true data generating function, but we only have the training set available of that. What does this mean? It means that we can use expectations. So if we anyway just have a sample of the data from your data generation function like the training set, it does not really matter how much of this data that we use for one pass of the optimization. So it also means we usually do not want to optimize over the whole data at one time step, even if it would be possible. So you're already very familiar with that, but this means what we actually use is so-called mini batch algorithms. So at each optimization step, we use a sample from our training set, which comes from one batch. We optimize this batch, and then we take the next sample of the batch size. So it just means we don't need a batch size of the size of the whole data set. So the question is then, this is not a parameter, how large should these batch sizes be? If you have large batches, you get better estimates. Why? Because you use more of your data. But maybe the cost does not increases more than linearly. So if your batch size is double the size that you used before, then maybe your cost is 4 times that much. If you have very small batches, then you might not utilize your hardware enough. So for example, if you train on a GPU, you would like to have as large patches as possible because the increase in computation time between a little bit larger batch is not very large. So because it all runs in parallel. So if you have 10 tasks in parallel or 20 tasks in parallel, it's the same time because it is in parallel. So you would like to make the batches as large as possible to use the hardware there. Usually in image processing, you will end up with some memory limit of your GPU memory. So if you only have only 12 gigabytes on your GPU and you have large images, then it will not be possible to process more than some images here. Actually, theoretically, if you have smaller batch sizes, they kind of have a regularization effect. But in practice, I would check with your GPU to use as large a batch size as possible. What we are actually looking for is then a minimum in our cost function, and ideally we would like to get to the global minima. But of course, we don't have an algorithm that looks for the global minimum. We only have an algorithm that looks for the local minimum through gradient descent. So we will make sure that the local minimum we will eventually find is maybe in the neighborhood of our true minimum. If we have some other local minimum which has a much higher value here, that would not be a good result. When you actually look what happens during optimization, so for example, if you look at the loss function, you would expect that the loss function at the end, or the error function, will be quite smooth when you have the minimum. But that usually does not happen. It will still start to wiggle around here. So also, you will not really have a gradient of 0 at the end of the training. Why would you have 0? Because you're in a local minimum. Local minimum, the derivative should be 0, but usually it's not, which just means you will move around the neighborhood of your local minimum even at the end of the training. So how do you find that local minimum in the first place? This is done by the stochastic gradient descent. So we said, okay, we take some mini batch of examples, and from this mini batch, we compute the gradient estimate, and then we apply the update to our weights depending on the gradient. So this is as the training works on the network. So if you apply the update here, you change your weights by a factor that is dependent on the gradient and some epsilon value that you multiply the gradient with. So this is commonly called the learning rate, and if you have a larger learning rate here, then your weights will adapt faster, and if it's smaller, then they will adapt smaller. But also, if they're smaller, they might not move that much. And at the end of the training, when you're near the global minimum, you don't want them to move so much. But at the beginning, you want to move them faster. So one possibility for that is that you decay the learning rate over time. So you start with a larger learning rate, and then this time you adapt that learning rate by a factor here. Sometimes even in some well-known problem, this is actually done by hand. Like in AlphaGo, they just decreased the learning rate 3 times during training. Manually, they just looked at the training, stopped, reduced the learning rate, and then continued to train there. So just a stochastic gradient descent is one possibility to use the optimization, but there are also some other optimization techniques available. One are the so-called momentum methods. What is a momentum? Momentum comes from the physics. So if something moves in a direction, then it has some momentum, and then it's a bit harder to stop it or to make it go somewhere else. And this is the idea with this momentum-based learning. So if you move in the direction that you are, then it will take a while to get you away from that direction. So these momentum methods, they just accumulate some average over some past gradients and then use that together with the new gradient to calculate the actual update. The idea behind that is that often you have some elliptical valleys, so you try to find the minimum here, but because the gradient here will not go directly to the minimum, but rather in this direction, and then in this direction, and then in this direction, it will move slowly to the minimum here, and with this accommodation you can make it go faster directly to the minimum here. Other possibilities is that you have some adaptive learning rates. So you have an optimization algorithm that learns how to adapt the learning rate itself, which can help a lot, and which can make it quite a bit faster. So there's different methods. One is AdaGrad, that just scales the learning rates by looking at the gradient that happened before. So because if the gradient is small, it will not change much. It will give some greater progress in the direction, so you have a small gradients. And RMS prop is quite similar, but maybe the update is done a little bit more smooth by exponentially weighting the moving average. And another well-known method is ADAM, that actually combines this adaptive learning rate here with some momentum from the last slide here. So the problem is a bit, then you really need to know the hyperparameters for effective use of some of those algorithms. Some work quite good out of the box, but if they do not work out of the box, then you're kind of stuck, and it's not so easy to get the hyperparameters first. So what I usually do is I start with stochastic gradient descent until the model converges at least a little bit. Maybe you don't want to run it until the end if it takes too long, but you know that your training actually works. And then you also know the learning rate that it works. So maybe you can first play a little bit around with the learning rate to see if you can make it converge faster. And then when you have the learning rate and you know that it works with everything else, then you can use AdaGrad or ADAM to just make it learn faster and start with the same learning rate that you have here. Okay, so what other options do we have in designing neural networks? Well, one is activation functions. We looked at that quickly. The most common activation function now is ReLU, which is just the x value on the positive axis and then a 0 on the negative axis here. There is some newer activation function, leaky ReLU, which has a slight advantage that on the negative axis here, the value is not constant, but it goes a little bit down. This has the advantage that you will actually compute a gradient, so that should be better with the optimization. But of all those activation functions, research has shown that actually ReLU works quite good. So I would use ReLU first and just check the learning rates if you have problems with the convergence of your functions. If you want, you can try out ReLU or something similar. Leaky ReLU or ReLU, it might improve a little bit. And sometimes tangency hyperbolicus can be good, but usually it's not so good. Why? Because similar to the sigmoid, it goes to -1. It has a very low gradient at some regions here, and this makes it harder to converge. So if you want to try leaky ReLU, it's for example also implemented in the Keras library here. Okay, then somebody mentioned in the beginning, weight initialization is another thing that you might have to look at. Why? What happens if the weights are too small? Then your activation are just 0, and then you just no learning. So if you start with 0 and gradient, it will just be 0. Just come back to the question then. If it's too large, then maybe you're way off on your result here, and then your gradients might not be too high either. There was a reason, so there was a question, why should you not use sigmoid for hidden layers? Well, one reason is that just ReLU works better, much better, so it will converge faster. The reason that it converges faster is the shape of the sigmoid function for large values of x. So sigmoid in this region here works quite well, so it's also similar to here. But if you have your x in this area here, then the gradient of the function here is very shallow. And because the gradient is very shallow, it will not improve much. So it needs a lot of steps to improve. While in the ReLU function, the gradient here is the same. It's very high. And so this will improve much. So the result is that the learning will go usually much faster with the ReLU function than with the sigmoid function. Exactly, thanks. So the gradient will vanish, and then you don't have, if you don't have a gradient, then just your learning kind of stops here. Okay, one more kind of a bit advanced method to make your learning better, that is something that came up from Google a couple of years ago, called batch normalization. What is the idea of batch normalization? We all know that at the input of your data, you should normalize your data always, right? Okay, the problem is that when your data travels through your network, it is kind of not normalized anymore. So because the outputs vary a lot during first to the stages of training, then the data can change a lot too. So suddenly the next layer has data that has a completely different distribution, and it might have difficulties to adapt. So the batch normalization is a method that will try to normalize the output of the of one layer during the training, so that the next input will always receive some similar kind of normalized data. So you could just insert it after convolutional and dense layers, actually before the activation function, because you want the activation function to respond to the normalized data here. And so this generally improves gradient flow and allows higher learning rates. And for example, in beginning in TensorFlow, it was kind of hard to use because you have to program it yourself, and that's not so easy because you have to maintain all your averages. But in Keras, you can just add it as a layer and you get it for free. The problem is a bit that when you then run it during test, you will need the learned values for the normalization, because you also have to normalize the data then when you just apply the equation. So what should you do with training a network? So when you see all these nice examples today out in the internet, you think everything is easy, you just make your network and it will just always work. But in general, this is not always the case. So you kind of have to babysit your process and adapt it a little bit until it optimizes and then it runs at their best speed. So what I usually try to do is I start with too little data. If you have too little data, you will expect that your model overfits, but also your model should converge. And so if your model converges, then you know that weight initialization is correct, your learning rate is correct, it just does something. So that's always good. And then you can add more data. Your results will be less good with the accuracy, with more data, and maybe you have more generalization error, but the network as a whole will work. Then if you use regularization, I would check the loss before and after regularization, just to make sure that you don't put too much loss in the regularization, because otherwise it will all the weights go to zero. That's not what you want. So I would usually adopt like 10 or 20% of the loss function to the regularization and 80% to the main loss function that you want to minimize. And if you look at hyperparameters, I would look at the learning rate first. So because really it takes a lot of time, so if it doesn't go down fast enough, you just want to try larger learning rate, because then it matters if you maybe wait for 2 days or if you have to wait for 2 hours. And so you can just do it by increasing it like 10 times or so. Maybe start with 0.001 and then try 0.00, 0.01 and so on in the directions until it works better. So also for hyperparameter optimization, if you have a lot of them, I would first use some core search of the parameters, and then you can adjust them a bit more fine. So that for me, I think that the most important hyperparameters to try out first, like the network capacity or the architecture of your network. You can also adapt that in several steps. So because maybe you added some more data, then you might need a little bit more capacity or more regularization, and then adapt that. Then of the other hyperparameters, the first important one to do is to adjust the learning rate, because you want to make sure that you use your computing time efficiently, so that that it actually converges. Then I will look at some regularization weights. So first, without regularization, so you have overfitting, and then just add the regularization to see that you have a good balance between overfitting and capacity. And I usually do regularization first, and then maybe add some dropout percentage if you want to use that. Just try it out and see if it's better. It works. In some cases, it works very well. In some cases, it has a little effect. And when you during your training, it's good that you can monitor some loss functions. You ideally want to do that during the training, and not only when the training is done, because you might have waited too long. So for example, if your learning rate is too high, if it's very high, it will just not converge. If it's too high, it will go in the direction of the minimum, but then it will just move around your minimum and never stay in the minimum. So it will not go more down. If it's too low, it's just too slow. And the good learning rate will get you fast in the vicinity of the minimum, and then let it stay there, that it still goes lower. And of course, you want to monitor your accuracy to check for overfitting. So if you have something like that, that's from an example. So this is the training accuracy and the validation accuracy. And here you just have a gap of 20%. So it's probably it's too large, so it's overfitting. So you should check the regularization. If you have no gap, then maybe it's all perfect, but maybe you don't have enough capacity, so you should at least try to increase the capacity. Maybe you can make both curves go up a little bit more. So maybe in order, even if you work from Jupyter notebooks, in order to monitor this accuracy during the training, one possibility is to use TensorBoard, which is a real-time display in TensorFlow that you can look at during training. And to do this in Keras, there is a callback function that is called TensorBoard, and you can just instantiate this callback, and then when you call model fit, you can give it this callback here. So it needs to be a vector of callback functions. There could be more than one. This would be the one for the TensorBoard. And it will just write some log files in some log directory. And in a separate process, you can then start the TensorBoard and look at the log directories there to have the real-time display. So you can display some scalars, loss functions, etc. I'll quickly see if I have some thing here that I can show you. Oh no, I started, so I cannot, but let's maybe just go quickly to the TensorBoard web page. So like, sorry, I don't have one running. So if you start TensorBoard, you will just get a display then in the browser, which can show you your weights distribution, your accuracy, and you could also visualize, for example, your network, how it looks like. I think the weight distributions are a bit more complicated to monitor, but the loss and accuracy functions, they can be monitored in real time, and that's a lot of help. Yeah. Okay, one more tip for homework. When you train your model, of course, you would like to save your model. So saving and restoring models in Keras is not so difficult. You can just convert your model as a JSON file. So you have to do it in 2 steps. You have to write your model, and then you also have to write the weights for your model. And then if you want to load the model again, you again need the model file and the weights file to have a running model again. If you want to do some more metrics for the results instead of accuracy, there's 2 possibilities. One is to just calculate the metrics after training, for example, the confusion matrix, and then you can calculate all the values that you want from the confusion matrix. If you want to have it at real time, it's a bit more complicated, as Keras does not support very many metrics directly, but it supports some callbacks to calculate the metrics by the backend, but that means you have to do it in TensorFlow, but in TensorFlow it has been made much easier in the newest versions. The problem with calculating metrics during training is that you need a function to update your matrix, because you only look at one batch at a time. Okay, so this was all from the first part of training networks. So for the texture recognition homework, some more things that you try out, maybe if you're already done. So for example, it could be that you would want more data. So I have a separate, an additional data loader in the Moodle. With the data as you port it with the normal loader, you will just get the center piece of the images, so that's not that many images. There is also another options will extract more tiles from the image so that you have more patches then to train. But I would first train with the smaller data set because it will converge faster there. Okay, so that this is all from sorry, otherwise you don't have the microphone anymore. So I would suggest we make a small break of 10 minutes and then start with the object detection. Okay, welcome back. Hope you had a nice break. So we will go on with our next topic. So the next topic will be finding and classifying objects. So what do we mean by that? So far, you have looked at two problems with classification in neural networks. So we have looked, or you have looked first with Sandro at classification of objects in an image. So you have one image and you want to find out which object is contained in that image. And then we have looked at the semantic segmentation, where we have a class for each pixel, and we have to try to find out which class that pixel is on a pixel level. So our next topic will be detection and classification of multiple objects in an image. So what you would have is some image that contains now more than one image, or more than one object, sorry, which are labeled, for example, just labeled by a bounding box, and you want to find out all the images that are visible in that, all the objects that are visible in that image. So here are some examples actually from a ground truth data set to learn such a scheme. So for example, you would detect the 3 chairs here, or the bicycle and the bottle here. Or here's just some results of one method that we look at, the RCNN, where you then just detect the dog, for example, here or here with some probability and all the other images. So this is the task, and I would like to again look at that a little bit from a historical concept also, so that we looked at what have people be doing before there were convolutional neural networks, and what can we do, what was the best what we can do now. So we will start today with some classical approaches to that problem. One such approach, very famous approach, is the Viola-Jones detector for faces. It could also be used for objects, and then we will also look quickly at the Hock detector to be used for people and pedestrian detectors. Then we will go on to more modern approaches. We'll quickly look today at the overfitting, which involves some things from classical approaches and combines them with neural networks, and then we go to the more really neural network based approaches that will be then next week, RCNN, faster and faster RCNN methods, and YOLO and SSD, and maybe one more approach here. Okay, so we will start with this Viola-Jones face detector. Why face detector? It is a well, it's a common problem. You want to, for example, maybe count people. You want to help when you take a photograph, where are the faces in the image. So it's in very many devices. Face recognition is already present, or has been present for a long time, but those devices are usually don't have very large computational power, and so you need a face detector that is both reliable but also very fast, and that was not that easy to do. So then in, I think it was like 2000 something, Viola and Jones, both from Cambridge, so from Merle, famous research lab, came up with their detector. And one of the main problems they had to deal with is how to scan many positions efficiently for the faces. So now we cannot just recognize in the image, okay, there is a face or there is no face. We have to detect them all and see where they are. So maybe if you just look a bit more broad on a standard approach, how would you do object detection for that kind of problem? Then your standard approach, you've already seen a little bit, would be you will probably calculate some features on your image, and then you can classify the image according to that features. And now if you want to do that for different objects in the image, then you will probably need a so-called sliding window approach. So you would just look at one part of the image, sub-window of your image, and see, can you detect the object in that window. Then you go to the next window, to the next window, to the next window. Problem is, of course, that you have many such windows, and maybe also on different scales, because your objects could be larger and smaller. So you have many sub-windows that you would like to classify faster. We will see then next week what other approaches exist besides the sliding window approach, but in the first classical approaches, this was what was mainly used. So how does this face detector deal with these challenges, and how does it apply this standard approach to object detection here? For features, it uses a specific set of features called HAR features, which are very efficient to calculate. As a classifier, it uses boosting, which is not used that much otherwise in machine learning, but which is quite popular in image processing computer vision tasks. So we will look at how this supervised learning classifier works. And in order then to make the sliding window approach more efficient, they use something called cascaded classifiers. So they will still use a sliding window approach, but try to minimize the processing time that they have in each window. So, okay, let's first look at boosting. So boosting is a supervised learning technique. That means we will have some training data. So let's assume we have some training data with positive and negative examples. If we, for example, just want to have two classes. In our case, that would be it's a face or it's not a face. A bit special in the boosting is your training data will have weights. It does not need to have weights at the beginning, but during the training it will get weights assigned, and such with higher weights have more influence than on the results. Boosting then works like that. You train what is called a weak classifier. We will look at that. A weak classifier classifies the data somehow, but it will not be perfect. It's not the idea that it's perfect. It might not even be very good, but it will be a bit better than just random guessing. Then we classify that using the weak classifiers that we have so far, and if there's any errors, we increase the weight on those errors of the samples that go to those errors, and with that increased weight, they will have more influence than on the next classifier. At the end, we get a combination of all the weak classifiers that we learned here, and this will then be our final classifier, which is a strong classifier, means it should have some sufficiently good metrics. So at the end, it will look like that. We have a strong classifier. Strong classifier means we get input of a function, and it will tell us which class it is. So for a binary problem, this is most usually done by the sign of the function here. So if it's minus, it is one class. If the sign is positive, it's another class. This strong classifier will be a linear combination of those weak classifiers, each with a weight and each with some classifier function here. And that weak classifier, we just, okay, here I just used 1 and 0 instead of -1 and +1, that it will have 1 if some measure calculated from the feature is smaller than some threshold, and otherwise it will be 0. Okay, let's look at some example here to make this more clear. What we have here is a training set of data with 2 labels. So label +1 of all the red data and -1 of all the blue data. We have some samples from our training set, and the idea is now we would like to train a classifier that can distinguish between the red samples and the blue samples. We will look at those weak classifiers of certain functions that will be linear classifiers. So each classifier will just be a straight line, and determine on which side of the line that the sample is, it will be one class or the others. As you can see, there is not a good straight line that will get a good result on this data set. So if you would just have the line in the middle of your data set, then it will just be chance. So if you're on the one side, on the other side, your error will also be 50% on average. If you move the line a little bit, then it's a little bit better than chance. So because maybe on the right side here, it's still the same amount of red and blue samples, but on the left side, it is better because you have mainly red samples. So this classifier will be better in its performance than just a random classifier. But it's a weak classifier because it does not perform very good. So what happens if you use it anyway? So the classifier then tells us everything to the left is red and everything to the right is blue. So there's some mistakes. There is a blue one on the red side, so this is a mistake, and many red ones on the other side are mistakes. So they they get their weights increased for all the ones that were wrong. The other ones that were correctly classified remain the weights. So now we have a new problem, and we again try to find another weak classifier that is a little bit better. So it's a weak classifier in combination with the classifier that we already have. So let's say this is our next weak classifier. So the combination of them will say to the left of here it's blue, to the right of here is red, and to the left of here it's blue, and to the right of here, to the left of here it's red, and to the right of here it's blue. So the combination gets less errors, but there's still some errors here in the middle section. Okay, some mistake here. There's also some blue errors here that should have a higher weight. Then again, we take the next weak classifier. This time, because those values have a lot of weight, it will be a classifier that tries to correct the errors here. And at the end, we have an additional classifier on the top. So we have 4 weak classifiers, and together they form a stronger classifier that is able to sufficiently classify the data set. So it's not perfect. There are some mistakes, some blue ones on the wrong side, but for example, all the red ones are classified correctly, so this is much better than each one of the weak classifiers. And so boosting is the technique to find those classifiers and combination of classifiers from those weak functions here. Okay, so now how can we use that in image processing? How are they determined? You will have to look at the paper. So this is more math involved that will deal those parameters so that combination is then optimal. So they're calculated in some ways from the weights of the sample data set. Okay, so the classifiers that we want to use in this Viola-Jones approach are filter responses. So you know what filters are, and you also know that filter responses are quite intensive to calculate. So for example, if you want all the responses of a m by m filter on an n by n image, then it's n squared times m squared, and if the filter is as large as the image, which sometimes can happen, then it's a n to the power of 4 algorithm, and that's quite intensive to calculate. So they wanted to use filters, but they wanted to use filters that are easier to calculate. So they use filters which are called Haar filters, or actually Haar features is then a combination of such filters. The idea is you have filters with a rectangular mask, and the filter kernels are just plus or minus 1. Okay, so for example, you could have filters with 2 values here or 2 regions here. You can also have filters with more regions, so they used 2, 3 and 4 different regions, and each region here means that this filter kernel is all plus 1 and this is all minus 1. So when you have a filter kernel of plus 1, if you remember how a filter operates, it will multiplicate the filter values with the pixel values and then sum it all up. And since the filter values are only 1, this would be the sum of all pixels in this region here. And this, on the other hand, will be minus the sum of all the pixels in that region. So the idea is then to use different filters on sub-images of times 24 by 24 pixels, and all different combinations of such filters as candidates for the features that should be used for the weak classifiers. But still, there's a lot of different combinations here. So why should we use those Haar images, Haar filters? Because they're particularly easy to calculate, and there is some trick for easier calculation. This is the so-called integral image. How does that work? Integral image is a preprocessing of your image, and every pixel in the integral image corresponds to the sum of all the pixels in the rectangle from 0 to that position of the original image. So this here is the sum of all that, and at the end this point here will be the sum of all pixels in the image. Well, how does that help? If you have the integral image, you can actually calculate the sum of any rectangular area in the image quite fast. So what you want is the sum of all the pixels in D, and you can find out that the sum of all the pixels in D is the sum of all those pixels minus the sum of those pixels minus the sum of those pixels. Now you have put region E, you have subtracted region E twice, so you have to add one additional region. So, and those regions are the values that you have at the integral image at that location. So at the end, the sum of D can simply be calculated from the integral image by the value at position 4 plus the value at position 1 minus the value at position 2 minus the value at position 3. So it's just a sum of 4 values instead of doing the expensive filter operation, which is of course much faster. Okay, let's have a quick example here. Okay, so this is just some example of integral image. So we will not use the exactly boosting or so, but just how those integral image and the HAR filters work. So what we have here is actually a sample image from some challenge for some teams. So at our school, every year there is some challenge in some module that they have built, some kind of a robot. And then there is a challenge at the end where they have to demonstrate. And last time they had to build a train, and the train had to recognize a number on a sign while passing at as large a speed as possible. So the idea was to detect those numbers here, and many approaches went to first detect the sign and then use some recognition on the numbers. And so what we would like to do is, can we use those integral image or those HAR features to detect the sign here? And if you just look at the area of one rectangle, then seems feasible that this region here will be the region that has the largest total sum of pixels, because it's mainly white here. And so we will see if we can calculate that. So this is our input image on gray level, and I can then calculate the integral image. The integral image will have the same size and just higher values here. So for example, the value at this position in the integral image will be all the pixel values in that region here. From this, I can calculate the HAR features, just as we said in the as we have seen in the slide. So in order to have the sum of all the images in that region, I only have to, I used some different values here. I only have to calculate those 4 values and then calculate that expression. And so to find the rectangle which maximizes that features, I go to all possible rectangles in the image. So that would be a sliding window approach, and I just calculate the value here of the HAR features, and if it's a maximum, I will keep the position. Okay, now if we do that, then we can actually see that we find the image here as a maximum, as those rectangles with the maximum sum, and the calculation is quite fast, even so I have to go through a lot of images here. I also tried it on the full image. There it's of course doesn't work that well because you have more white pixels here. So this rectangle has a higher sum than this one because that has some black pixels here. Okay, that was just some idea to show how these integral images work. Okay, so now we have a feature detector. This is, or possible features. Each feature is a classifier, and the idea is that we want to find out which of those features work best on the sub window. So the idea is now that we use these boosting techniques, special version called data boost, just how it is calculated, and train then the combination of feature responses that works well for classifying faces. So the idea is you just have all these face images, you have all possible features there. Yes, I can upload the notebook here if you're interested. You have all these possible filters here, and which filters have a high impact on determining if this is a face or not. Well, what you think? You could look at some features. Some might make more sense for a face, some not. So for example, this here is probably not a good candidate, while something around the nose or the eyes or so could be more helpful in deciding if it's a face or not. So they did all that. So they used all 160,000 responses as features and then train the other boost to find best features for classification. And the results were those two features. So this filter and this filter together are strongest to determine if it's a face or if it's not a face. Okay, but altogether they used I think 200 of those detectors then to actually classify the image. Okay, so we have the feature detector, we have the classification, and now we can just apply it on a sliding window approach. There is one more challenge, is that still, even it's very fast, but it still needs some time to calculate this in every sub window. So maybe can we speed this up a bit? And they came up with the idea of using a so-called cascaded approach. The idea is that in all the sub-windows that you look at, faces are relatively rare. So they maybe have 10 to 12 faces per image, but a large majority of positions that you will check will not have a face. So can you come up with some measure that you could omit those regions without spending too much effort, and then maybe spend more effort on the regions where you said there could be a face? So all in all, they wanted to have a high true positive rate of about 90% of really detecting a face when it's actually there. And they want to have a low false positive rate, that they say somewhere, okay, there is a face, but it's not actually a face there. And for that, they use the cascade of classifiers, and this has the effect that these positive rates and the false positive rates and the true positive rates in those cascades multiply. So it goes like that. You have you look at all the sub-windows in your images, and you have a first classifier that says, okay, it's not a face, or it might be a face. If it's not a face, then it's not a face and you're done. If the first classifier says it might be a face, then you give it to the second classifier, who will check again with different feature values and again determined, okay, if it's not a face, it's not a face. If it might be a face, it will give it to the next classifier, and so on and so on. So at the end, 10 classifiers have to say it is a face, and then it's considered a face. And if one of them says it's not, then the window is rejected. So how can you make those classifiers? The idea is you can make the individual classifier steps in the cascade relatively weak. They must have a very high true positive rate of 99%, but they can have a relatively low false positive rates. So false positive rates that they say, okay, it's a face, but it's not actually a face. But here you don't want to miss any true faces in the images. And with those goals for each classifier step, you can then calculate what you get with a cascade of 10 of those classifiers behind each other. So your true positive rate, if you then take it to the power of 10 because they multiplied, will still be 90%, while as your false positive rates from your 0.3 to the power of 10 will be very small, and so you could then fulfill the goal. And the idea is then you use only some of the features in each classifier step, so you reduce the processing time there. They use this as a training data, and here are some results then from the original paper, which works quite good. Not in all cases. So Scotty is missed here in Star Trek. Here face missed here. Here there is all also in different resolutions. I have a little animation of how it works. Going through the faces, let's see if this runs. Okay, so this is just the idea then how this classifier works. So it will just go through all the sub windows and use all those learned features then to classify the sub window. And so for some parts it will have to go through more stages of those cascade, and for some windows it can reject it very early and then move on to the next one. Okay, I will try to move it forward a bit. So in that region where you actually have the face, then the classifier, the cascade takes much longer, because it will have to go through all those 10 steps, because there is actually a face there. And so here it will display the maximum values of the faces that are found here. Okay, so for a long time this was like the best face detector. Even now, if people ask on the internet of the face detector, best face detector, people suggest Viola Jones, but in the meantime there are some other approaches available, and it was really a usable approach. So it has been implemented then in a lot of devices and cameras, and so because it had a relatively low computation time. What doesn't what's not so fast is the actual training time for the cascade and features. This can take days to weeks. So you could use the same approach not only for face detection, for detecting any other objects. So this is a general cascaded classifier approach to object detection, which used to be the standard, or one of the standards, before the neural networks came along. Meantime, so just one example. So this is one more recent publication on face detection. So they use a convolutional neural network to detect faces, and especially small faces. And I think this is quite impressive what can be done now. Okay, so this was one example of object detection approach. We will quickly look in a bit less detail now at the two other approaches, before then going next week to the neural network based approaches. One other large area of research for detection was pedestrian detection. So for autonomous vehicles and other applications, this has been studied for like 20 30 years, and the idea is then to detect people in those images. So you have again only one type of object, people, that you want to detect efficiently here. Maybe the classifier approach might also work here, but you might have need some different features tuning here. So one standard approach for that for a long time was to use the histogram of gradients for human detectors. And this again follows like the general object detection pipeline, I would say. So you have a feature detector for that it was the histogram of Gaussian descriptors that we have already seen, that you can calculate on the image. The idea here is you calculate it already in blocks, and this will help you a little bit then with the sliding window approach. So when you then look at the specific detection window, you can just collect the histogram of gradients that intersect your detection window. Then you have the features in your window, and then you can use a linear support vector machine for person and non-person classification. So this was all outlined by one paper from I think 2005 or so, for those histograms of orient gradient, which then proved to be like the best pedestrian detector for the next years to come. We already looked at those HOC descriptors. So if you remember, those HOC descriptors, they are calculated in some block of your image, and then each block will give you those histogram. So then when you look at some specific window, you can just look at all those features that you have here in those blocks. Here is a visualization then how these blocks are used in the support vector machine. Okay, sorry, error here, should be a M. So for example, these blocks are more important as positive examples for the support vector machine, and here you can then also see the directions that the gradients need to have for those blocks to be important as positive examples. And here are some blocks that are specially selected for negative samples for the support vector machines. So for example, if you have some gradient in the middle here, then that will probably not be a pedestrian. Okay, so that was one. It was a bit quicker. One approach with just feature descriptors, HOC interface, support vector machine classically, and a bit the trick here is that you can use the HOC descriptors to more quickly calculate sub-windows, because you can pre-compute them on the whole image here. So then from here, the next approach that was tried for classification was then naturally to use neural networks. So our feature is from 2014, and they try to combine then the classification, the localization, and the detection. In their approach, they still first used a kind of sliding window approach together then with some neural network to also predict bounding boxes. We will see then next week in the lecture that the more modern approaches use that more consistently together to first then use the network to predict possible bounding boxes of your image here. So for classification, they used a convolutional neural network similar to the AlexNet that that just won the ImageNet challenge the year before. That's quite a large network with large windows. They modified it a little bit because the original AlexNet had a subsampling factor of I think 36, so it made the input 36 times smaller, which is then not good if you want to try to find multiple objects in the image. So they reduced it to 12, which basically means that with a sliding window approach you can apply that every 12th pixel. So you cannot detect objects which are nearer than 12 pixels or smaller than 12 pixels, because your image will be reduced to that after the convolutional part. So, but they just on every sub-window, and they use sub-windows of different scales, then they apply a classification. So for each sub-window, then they have a class that they have calculated. As a next step, they generate bounding box prediction, and for that they again use a convolutional neural networks, and they use actually the same convolutional networks, or the first few layers of the convolutional networks as the same, and then trained a regression part of the network to generate bounding box predictions. So we will also see next week, this is quite common to reuse the network for different tasks. This helps you with the computation. So you look at those first 5 layers as a feature descriptor that will calculate features using your convolutional networks, and then you use those features first to classify what object could it be in that region, and to generate the prediction of the bounding box of possible objects there. So what you get as a result of this step then is you get a large number of bounding boxes that are predicted then as output. And in a final step, then they combine the classification and localization by merging and accumulating bounding boxes. So what they have is they have the bounding box, then inside the bounding box they have the different regions that were determined from the classification from each subregion in the bounding box, and they know which class that it is, and so they if it's all the same class, then they will combine those bounding boxes and accumulate them, and then delete the smaller ones that are inside there. So at the end of that process, they will end up then with one bounding box for an object and the classification result for that object. So this is like the first approach that uses convolutional neural network. As I said, still with the sliding window, first to try to classify every possible sub-window with a convolutional neural network. But this OR feature, that paper then won the localization challenge of ImageNet in 2014 as the best method to identify and localize objects. Okay, so this is actually all then for today. So for the first part of the object detection, and next week we will look at further techniques that use convolutional neural networks for object detections. First the RCNN family of algorithms, and then the so-called one-shot detectors that will immediately try to find bounding box and object classification in one step. Okay, any more questions so far? I have not done a separate exercise for today, so the idea was that you maybe would like to continue with the homework, and that I can also be here and answer some questions about the homework. I will upload the solution for from last week, so that you could use that as an input then also for your homework. Otherwise, have a nice week, and see you next week. Bye-bye.